Hello. Previously, we discussed the symmetry transformation of Lagrangian and some properties of Lagrangian formulation. Okay. We also discussed Noether's theorem in order to relate infinitesimal symmetries or continuous symmetries and corresponding constants or invariants of motion. Now, our target or our objective is to write down the expression of the Lagrangian of a free particle and a system of particles. Okay. Now that will be done in two parts. So in this, in the first part, which will be the second subpart of the lecture number 9 of Physics 401A, I will just start by giving you the concept of how to talk about, or rather how to develop the concept of inertial frame of reference, and also to get back or recover the law of inertia in this current Lagrangian framework, and also how to talk about or how to how to obtain the Galilean relativity, how to realize the Galilean relativity in the current framework. Okay. So as you all know that in Newtonian mechanics, the choice of frame of reference is of primary importance, right? In order to describe the motion of something. And of all type of frames of reference, inertial frames of reference, they have a specific meaning, or they are particularly very important subclass, because we all know that these are the frames where Newton's law of motion hold good, right? Now, and actually we don't need to introduce any additional source of interaction like a pseudo force or any artificial thing in order to make the Newton's second law valid, right? The Newton's second law is automatically valid, naturally. Okay. Now, here in the following, we develop the concept of inertial frame of reference without having recourse to the Newton's laws. So let us first assume that we do not know the Newton's laws. We just know the Lagrangian. Okay. And we also know that some symmetry properties of Lagrangian, that's it. Okay. Whatever we have already seen using Newton's law, we cannot use here. For example, L is equal to T minus V, right? That I started the derivation using F is equal to minus gradient of V is equal to mr double dot, right? So that we cannot use here. Okay. Now in the current approach, we develop the concept of inertial frame of reference using some properties of space and time. Okay. And here our objective is to find a frame of reference. So basically, before, the objective was to find a frame of reference for which Newton's law were valid. Now here we just want to find a frame of reference in which the laws of mechanics take their simplest form. Okay. Now simplest form simply means that unnecessary complications. So anything which is non-intuitive should not come in the description. Of course, you understand that simplest form doesn't have any concrete mathematical meaning. It is very subjective, but somehow something which is not really very intuitive should not be entertained. That is the message. Okay. Now at the first step, without any restriction, one can reasonably think that the nature of space and time can depend on the frame of reference. For example, if I talk, with respect to one frame of reference, the space and time can be homogeneous, but the space cannot be isotropic. In the second frame, the space can be homogeneous, but the time is not. Okay. And the space may be isotropic or not. Okay, whatever. So arbitrary type of combination can be possible, and of course there can be some frames of reference where nothing is homogeneous or isotropic. Okay, so in an arbitrarily chosen frame, there is no reason that the space is homogeneous, isotropic, and time is homogeneous, right? There is no reason. Okay. And what will be the problem if we have that? For example, if we now assume a particle without any other interaction is at rest at some time instant, then it is possible that only because the time is not homogeneous, at the next instant, just due to the inhomogeneity of time, the particle will start moving. Okay. Although we cannot see any direct agent or any direct interaction which basically makes the particle move, right? Of course, we can say there is nothing problematic here because this is not violating the fundamental cause-effect relationship of physical phenomena. We can say that, okay, we cannot see anything, but the cause is basically the time property itself, right? So there is a cause, there is an effect, there is no problem. But the thing is that then in order to mathematize that properly, that would make some, very thorough effort, and sometimes the effort is not very much schematic in the way that you cannot make a generalized prescription in order to describe all such type of inhomogeneous or erratic behavior due to inhomogeneity of space and time and anisotropy of space. Okay, so that could unnecessarily complicate the description of motion. That is the problem. So for the sake of simplicity, one should of course pick up a frame of reference where the space is homogeneous and isotropic and time is homogeneous. Okay, so in our premise or in our framework, we call this frame of reference as an inertial frame of reference. Remember, once again, we do not have any force concept over here. We do not have any Newton's second law or Newton's first law. We just have some properties of space and time, and we just use that in order to define inertial frame of reference. Okay. Now, you can see that it is not somehow guaranteed that such type of inertial frames in general exist. But however, that means that there is no theorem by which you can rigorously prove the existence of such frame of reference in general. Or maybe that is extremely difficult, even if exists. Okay. But however, in practice, frames are found where a particle at rest remains at rest. And experiments lead to same type of results when the entire setup is shifted in both space and time, and also the total setup is rotated or is oriented to an arbitrary direction in space. We can see that the experimental results are always the same. So from that, we can easily understand that although we don't know mathematically this always exists or not, but in practice, there is always a possibility to find such a frame of reference. Because we are physicists, so we will not we will be not waiting for the theorem to be proved in order to have the existence. If we find that in practice, we will take it. Okay. Now, these frames are chosen as inertial frame of reference. That's for sure true. That's our objective. Now, how to get back or how to obtain the law of inertia without using Newton's laws, or without stating the Newton's law in its usual form. Okay, how to get this coming from the Lagrangian. So first recall the Euler-Lagrange equation, this one. Okay, ddt of del L del V minus V vector. Okay, so this is nothing but the partial derivatives with respect to every component of velocity, minus del L del R vector is equal to 0, right? That I can write for a free particle for which there is no constraint. So I can simply say its natural coordinates or usual coordinates are nothing but the set of generalized coordinates, and the same for generalized velocity. Okay. Now note that above means in the above section, we have defined inertial frame of reference without using the concept of force and N2L, right? Now we will derive N1L based on our aforesaid premise. Okay. Now in our framework, Lagrangian is something which is supposed to be the fundamental to describe the motion of a particle. So That is something you have to understand here. So Lagrangian is something, so here we don't have the equations of motion because we are not going through Newton's laws, right? We will say that Lagrangian is something which is the holy grail, right? And it has all the information which can describe the motion of the particle of a mechanical system. If one somehow knows the mathematical functional form of Lagrangian and uses this equation, okay, that you have, okay, then only you can find in some way, okay, q as a function of t and q dot as a function of t, and finally you can describe or specify the state of a mechanical system. So let us first consider a free particle, that is a particle with no interaction with others. That means in its own universe it is the only entity. We now try to find what information we may gather for the motion of that particle in an inertial frame. Now, since in an inertial frame the space and the time both are homogeneous, and also you can see that when some observer is sitting on an inertial frame of reference and it is also seeing the motion of another particle which is not interacting with any other thing, then there is an intuition which should come that maybe that, I mean, the motion of the free particle, okay, the motion of the non-interacting particle should also reflect the homogeneity of space and time and also isotropy of space, right? That is because if you just think that, once again, because finally we want to avoid all the complexity arising due to the inhomogeneity of space and time and anisotropy of space. That's the thing. Now, of course, if there are interactions, then one cannot avoid all such effects. Okay, but if effects means some unnecessarily changing, change of state of motion or something. But here, for example, when the particle is freely moving and some observer is studying its motion from an inertial frame of reference, it will simply see that as for the observer the space is, for example, homogeneous, then the particle's motion should not involve any dependence on its instantaneous position, right? So whether the particle I am seeing here at Kanpur or I see at Bangalore, that should not make some difference if I see at the same time, of course, right? Okay. Again, if I am just saying that if I do the whole experiment, okay, now for freezing the space, let's say at Kanpur, and I do it today and tomorrow, should it change? If it's a free particle, there is no interaction. Intuition says no, it should not change because it doesn't have any external interaction. Okay, so nothing external is there, so time should also be homogeneous. Okay. So that's why the corresponding Lagrangian of the free particle should not explicitly depend. So that is very important point you have to understand. Should not explicitly depend on the instantaneous position coordinates and the time coordinates. Right? We all know that Lagrangian is usually assumed to be a function of q dot t and here r vt, as I just said. So using homogeneity of space and time, we can simply say that what else on which the Lagrangian can depend? Only v vector, right? And we call that Lagrangian as LF for free particle. Okay, that will be just a function of v vector. Now we again consider the motion of the particle in real space, which is isotropic with respect to the frame of reference because the frame of reference is inertial. Then whether the particle is moving along a certain direction or not, or whether it is moving along north or east or west or south or any arbitrary direction, does it really change the particle's velocity or the particle's state of motion? Should it? Should it? Because it is not again interacting with anything. Well, the answer is again intuitively no. Then we can simply say that the Lagrangian should ideally depend on the modulus of the velocity vector, of course, I mean measured from some origin. That's very important. Okay, and this we just in general write as v, small v. Okay, it is the speed, and once I can write this, we can write that this is also a function of v square. Every v you can write root over v square, right? So the scalar part of v, actually the magnitude of the vector v. So then this is another way of writing the Lagrangian of a free particle will then be a function of the speed square. Okay. Now remember, we have this equation 1, this one, okay, Roman 1. Now we said that L will be independent of R, so this term will be 0. So ddt of del L del V will be 0 as well. So del L del V will be a constant of motion. Now L, in general, although we have not said anything, but we just, whenever we said the method of the calculus of variation, everything, we always somehow tacitly assumed that L is a scalar. Okay. So if L is a scalar, then del L del R will simply be the gradient of L, which will be a vector. So that will be 0. So del L del V, which is also which will be a vector. So that will be constant of motion, and so this will be a vectorial constant of motion. Okay, and that constant we can call it as C. Okay. Now del L del V can be always written, if you just think a bit, you can easily see some arbitrary function f of v square times the v vector, and this is constant, and that is only possible when the v vector itself is a constant. So we can see that some particle which is not interacting, if its Lagrangian is totally obeying all the homogeneity and the homogeneity properties of time and space and the isotropy property of space, then we finally are left with this conclusion that v is a constant, and that's completely consistent with the first law of Newton, which is the law of inertia. Okay, so we conclude that in an inertial frame of reference, in our premise, okay, the velocity of a free particle is a constant vector. If it is 0 at any instant, it remains so. If it is non-zero constant, then it remains so in time, right? That is the first law. Finally, we talk about Galilean relativity. So just now we have seen a free particle moves with uniform velocity in an inertial frame of reference. Now let us assume another frame of reference be attached or fixed to the free particle. Since the Lagrangian of the free particle already is consistent with the space and time homogeneity and spatial isotropy, it is very reasonable to expect the reference frame attached to the free particle to be also an inertial frame of reference. It is like this. So let's say the frame of reference was studying a freely moving particle. Now freely moving particle was moving with a uniform speed v along positive x direction, for example. Now with respect to some observer which is now sitting on this freely moving particle, we'll see the old old frame of reference to be moving with a uniform speed minus v, or that means with the uniform speed v along minus negative x-axis, right? So you can see that if with respect to one the other is moving with a uniform speed, then with respect to the other, the first one is also moving with uniform speed. So philosophically these two are equivalent. So if one of them is basically inertial frame of reference, the other should also be reasonably an inertial frame of reference. Okay. So in practice, it is found that all the laws of physics, of course non-relativistic here, are same in any inertial frame, and another one moving with this inertial frame of reference with respect to this inertial frame of reference with a uniform speed with a uniform speed which may or may not be zero, right? So that simply says that all the frames of reference which are moving with respect to one and another, okay, with respect to one another, just by a uniform speed v, that v can be anything, okay, zero or non-zero, they are all known as the inertial frame of reference. Okay. So it also says that there can be an infinite number of inertial frame of reference. And also we can say that all the frames of reference, they are philosophically equivalent. So finally, in the description of the motion, they should not have any inconsistency. That I will just explain in more details now. So there should not be any preferred inertial frame. Okay. Now, in order to understand why the basic description of motion should not be, affected by the choice of inertial frame, that's simply because if the coordinates of the particle in two reference frames k and k prime are r and r prime, where k prime moves with a velocity v with respect to k, that means with a speed v along positive x-axis, for example, for simplicity, okay, just one dimensional motion, okay, then we can write, okay, here you can just take general three-dimensional motion, just a velocity v with respect to k, then we can write, okay, r is equal to r prime plus vt, where v is a constant vector. And the second thing is nothing but an assumption. So first one we just said from our construction. Okay. The second thing is an assumption, and we assume that t in the unprimed frame and the prime frame, they are the same. So that is the fundamental assumption of non-relativistic mechanics. It's called the assumption of absolute time. Okay. Both of these together defines the rule of Galilean transformation. Okay. Now, if one differentiates r twice with respect to t using a and b, we can simply say that d2r dt2 will simply be d2r prime dt prime 2. And we also know that if we now just think inside our mind that what Newtonian mechanics says, that the dynamic starts from d2r dt2 level. So from the point of view of dynamics, basically these two are equivalent. Okay, but we will now not using Newton's law in general. Okay, we will not be using. Okay, so in our premise, now again forgetting Newton's law, we simply say that from experimental observations, it is hard to distinguish between k and k prime. Okay, so two frames moving with a uniform speed v relative to each other are completely equivalent, and that is the fundamental principle of Galilean or non-relativistic relativity. Okay, so Galilean relativity, that is another relativity. Okay, so here I end this lecture. In the next lecture, I will be extending this discussion in order to derive the expression of the Lagrangian of a single particle, free particle, and also a system of free and interacting particles. Thank you.